Hi, my name is Qui Vo, and this is my mini project for CS438. Um, so, welcome everyone. Today, I'll be taking you on a journey through the evolution of TCP congestion control, starting from the original explicit congestion notification proposed by Sally Floyd in 1994, which is the main paper I'm using, and all the way to its cutting edge implementations in data center TCP, which is uh, proposed by Alizadeh in in a second paper that I'm using for this presentation, and I'll put reference in my final slide. I'll call data center TCP as DC TCP for short, and then we'll also explore the F4S, which is the latest or the most modern applications of ECN. We'll explore how ECN allows us to avoid packet loss, reduce latency, and still maintain throughput, which is critical in today's high performance networks. All right. So originally, TCP relies purely on packet loss to detect congestion. This means that routers drop packets only when buffers are full. This drop-tail mechanism often lead to long delays, unnecessary retransmissions, and inefficient network usage. TCP's response to loss by cutting the congestion window in half was also quite drastic. Therefore, it raised a fundamental question. Could we signal congestion before dropping packets? This question led to active queue management, or AQM. Early techniques like DEC bit, or Digital Equipment Corporation bit, and RED, or random early detection, try to signal congestion before buffers overflow. Um, RED probabilistically drop packets at queue's crow. Sally Floyd then extended this concept. What if instead of dropping, we could mark packets to signal congestion? That's where ECN comes in. Explicit congestion notification. So ECN adds a 2-bit field to the IP header. Routers that experience congestion mark these packets with a CE code point instead of dropping them. The receiver echoes this signal back using the ECE bit in the TCP ACK. Then the sender reacts by reducing its congestion window and setting the congestion window reduce flag, or the CWR flag. All this happens without dropping a single packet. So Floyd emphasized a few core design principles. First of all, uh, a single ECN mark should trigger a response, so no need to wait for a threshold. Secondly, to prevent overreaction, the sender should respond once per RTT, not per mark. Importantly, no slow start penalty. The ACK clock should be preserved to avoid pausing transmission. And last but not least, standard controls are preserved, as timeout events still trigger slow start as before. These guidelines ensures that ECN maintains TCP's responsiveness and stability properties while being gentler in loss-based control. Floyd's simulations showed compelling benefits. Telling traffic saw major latency reductions, throughput remained high, yet buffers could be half the size. And because there's no packet loss, retransmissions were avoided entirely. The takeaway? ECN offers a smarter, more efficient form of congestion signaling. So that's the basic uh, principles of ECN. So fast forward to 2010, data center networks pose a new challenge: ultra low latency, shallow buffer switches, and 10 to 100 gigabyte per second links. The challenge was that microsecond RTTs, massive throughput, and limited buffering create vulnerability to incast, collapse, and loss bursts. Uh, that's where Alizadeh, the author of the second paper that I'm referring to for this presentation, and his colleagues introduced DC-TCP, or Data Center TCP. It builds on ECN but takes a more refined approach. Rather than reacting to a single mark, it computes the fraction of marked packets to gauge congestion. In particular, they implemented a shallow marking technique, where switches mark all packets when Q exceeds a tiny threshold K, enabling immediate and quantitative feedback. Oh, here's how specifically uh, here's specifically how the DCTCP works. The sender calculates the congestion level alpha based on how many bytes were marked with CE. Then it adjusts the congestion window proportionally using this formula I'm showing here on the screen. If only 10% of packets were marked, the window shrinks by just 5%, for example. That way, the sender responds smoothly, avoiding unnecessary slowdowns. As you can see here in the graphs, traditional Windows reductions is always very high, while with TCP, DC TCP, the reduction is adjusted in proportion with the congestion level alpha, avoiding overreaction to transient congestion. So DC TCP achieves near zero queuing delays, maintains its full throughput, and dramatically reduces queue oscillations. The graphs in this slide shows how DC TCP keeps buffer occupancy low and stable compared to the traditional TCP. Its ability to absorb microbursts without loss makes it ideal for modern data centers. Uh, so here in the graph, this oscillations right here represents the standard TCP occupancy, and this blue lines down here represents the DT TCP queue occupancy. So huge difference. Next up, the latest evolution is L4S, also known as low latency, low loss, scalable throughput. It extends ECN to general internet traffic. TCP brag, a key algorithm here, which adjusts the sending rate in tiny increments, making recovery time independent of flow rate, even at 100 gigabytes per second links. Uh, Routers use dual queue, which means that traffic goes to one queue and L4S traffic to another. Capacity is shared fairly, while L4S maintains ultra low latency. L4S also uses immediate marking, which means that L4S queue marks packets immediately the moment congestion begins, thus avoiding threshold delay and forcing rapid sender response. So L4S uses two queues but shares capacity dynamically to ensure fairness. Classic TCP doesn't suffer, but L4S flows get immediate congestion feedback. Through L4S protection mechanisms, if a non-compliant flow tries to cheat by using L4S code points, the router detects persistent queuing and takes action to protect the system. As of 2023, L4S is already standardized via IETF RFCs. It's already implemented in Linux, FreeBSD, and cable modems like DOCSIS 3.1. Testbeds also show huge gains. 99th percentile queuing delay drops from over 5 seconds to just 132 milliseconds. So very huge improvement right there. Um, L4S is also paving the way for cloud gaming, AR, VR, industrial automation, or any area that involves internet networking that you can think of in this modern age of technology. So to wrap up, ECN began in 1994 as a clever idea from Floyd to mark instead of drop. In 2010, DC TCP showed it could enable low latency, high throughput control in the data center. And now, with L4S, we're applying those exact same principles to the entire internet. What started as a tweak to TCP is now foundational for real-time, high-bandwidth applications. And here are the key papers from Floyd and Alizadeh and other references that are used throughout this presentation. If you are interested in deeper dives, I highly recommend the DCTCP SIGCOMM paper and the recent IETF L4S RFCs. Thank you for listening.